Welcome back to a new session of the MOOC on information security. Today we will discuss data encryption standard. The objectives of this module are to give an overview of the history and structure of DES, to discuss the strength and properties of DES, and to understand the security of DES. The Data Encryption Standard or DES is a system developed for the US government intended for the use of public. It has been officially accepted as a cryptographic standard in many countries. The DES is a complex combination of two fundamental building blocks of encryption such as substitution and transposition. The strength of this algorithm is the result of a repeated application of these two techniques, one on top of the other, for a total of 16 cycles. History of DES. The Data Encryption Standard or DES is a symmetric key algorithm for the encryption of digital data. Although it has a short key length of 56 bits, make it too insecure for applications. It has been highly influential in the advancement of cryptography. Developed in the early 1970s at IBM and based on an earlier design by Horst Feistel, the algorithm was submitted to the National Bureau of Standards or NBS following the agency's invitation to propose a candidate for the protection of sensitive unclassified electronic government data. In 1976, after consultation with the National Security Agency or NSA, the NBS selected a slightly modified version or strengthened against differential cryptanalysis but weakened against brute force attacks, which was published as an official Federal Information Processing Standard or FIPS for the United States in 1977. The publication of an NSA approved encryption standard led to its quick international adoption and widespread academic scrutiny. Controversies arose from classified design elements, a relatively short key length of the symmetric key block cipher design, and the involvement of the NSA raising suspicions about a backdoor. The S boxes that had prompted those suspicions were designed by the NSA to remove a backdoor they secretly knew, that is differential cryptanalysis. However, the NSA also ensured that the key size was drastically reduced so that they could break the cipher by brute force attack. The intense academic scrutiny the algorithm received over the time led to the modern understanding of block ciphers and their cryptanalysis. DES is insecure due to the relatively short 56-bit key size. In January 1999, Distributed.net and the Electronic Frontier Foundation collaborated to public break a DES key in 22 hours and 15 minutes. There are also some analytical results which demonstrate theoretical weaknesses in the cipher, although they are infeasible in practice. The algorithm is believed to be practically secure in the form of triple DES, although there are theoretical attacks. This cipher has been superseded by the Advanced Encryption Standard or AES. DES has been withdrawn as a standard by the National Institute of Standards and Technology. Structure of DES. The Data Encryption Standard or DES is a symmetric key block cipher published by the National Institute of Standards and Technology or NIST. DES is an implementation of a Feistel cipher. It uses 16-round Feistel structure. The block size is 64-bit. Though the key length is 64-bit, DES has an effective key length of 56 bits because 8 of the 64 bits of the key are not used by the encryption algorithm and function as a check bits only. Though the initial key consists of 64 bits, before the DES process even starts, every 8th bit of the key is discarded to produce a 56-bit key. That is, bit positions 8, 16, 24, 32, 40, 48, 56 and 64 are discarded and used as check bits. The user can change the key at any time whenever he feels some uncertainty about the security of the old key. The algorithm uses two techniques to conceal information such as confusion and diffusion. That is, the algorithm ensures that the output bits have no apparent relationship to the input bits and spreading the effect of one plain text bit to the other bits in the ciphertext. Substitution provides confusion and transposition provides the diffusion. Substitution is sometimes represented by S boxes, which are table driven substitutions. Permutation, which accomplishes diffusion, is called P boxes. In general, plain text is affected by a series of cycles of a substitution, then a permutation. The general structure of DES is depicted in the figure given here. DES uses only standard arithmetic and logical operations on numbers up to 64 bits long. So, it is suitable for implementation in software on most current computers. Although complex, the algorithm is repetitive, making it suitable for implementation on a single purpose chip. The basis of the DES is two different ciphers applied alternatively. Two weak but complementary ciphers can be made more secure by being applied together, called product of the two ciphers. After initialization, the DES algorithm works on blocks of data. It splits a data block in half, scrambles each half separately, combines the key with one half and swaps the two halves. This process will be repeated for 16 times. Although the bit level manipulations of the algorithm are complex, the algorithm itself can be implemented efficiently. A cycle in the DES algorithm is shown here. Input to the DES is divided into blocks of 64 bits. The 64 bits are permuted by a method called initial permutation. The data bits are transformed by a 64-bit key, of which 8 bits are used as check bits or parity bits. Then begin the sequence of operations called a cycle. As shown in the figure, the 64 permuted bits are divided into a left half and a right half of 32 bits each. The key is shifted left by a number of bits and permuted. The key is combined with the right half, which is then combined with the left half. The result of these combinations becomes the new right half and the old right half becomes the new left half. The DES algorithm is given here. These are the sequence of activities in a cycle or round, and that is repeated for 16 times. After the 16th round, there is a final permutation, which is the inverse of the initial permutation. Steps for encryption can be summarized as: permutate the 64 bits in the plain text and divide them into two equal halves. These 32-bit chunks of data will undergo multiple rounds of operations. Apply XOR operation in between expanded right plain text and the compressed key of 42-bit size. The resultant output is sent to the further step known as S-box substitution. Now apply the XOR function to the output and the left plain text and store it in the right plain text. Store the initial right plain text in the left plain text. Both the LPT, that is left plain text, and RPT halves are forwarded to the next rounds for further operations. At the end of the last round, swap the data in LPT and RPT. In the last step, apply the inverse permutation step to get the ciphertext. Steps for decryption. The steps involved in data decryption are: the order of the 16 48-bit keys is reversed such that the key 16 becomes key 1 and so on. The steps for encryption are applied to the ciphertext. Since DES is based on the Pfister cipher, all that is required to specify DES is initial and final permutation, key schedule and round function. The initial and final permutations are straight permutation boxes or P boxes that are inverses of each other. They have no cryptographic significance in DES. The heart of this cipher is the DES round function F. The DES round function applies a 48-bit key to the rightmost 32 bits to produce a 32-bit output. Since write input is 32-bit and round key is a 48-bit, we first need to expand write input to 48-bit using expansion permutation box. After the expansion permutation, DES does XOR operation on the expanded write section and the round key. The round key is used only in this operation. The S boxes carry out the real mixing or confusion. DES uses 8 S boxes, each with a 6-bit input and a 4-bit output. The 32-bit output of S boxes is then subjected to the straight permutation. The round key generator creates 16 48-bit keys out of a 56-bit cipher key. Some key features affecting how DES works include the following. Block cipher. The data encryption standard is a block cipher, which means that a cryptographic key and algorithm are applied to a block of data simultaneously rather than one bit at a time. To encrypt a plain text message, DES groups it into 64-bit blocks. Each block is enciphered using the secret key into a 64-bit ciphertext by means of permutation and substitution. Several rounds of encryption. The DES process involves encrypting 16 times. It can run in 4 different modes: encrypting blocks individually or making each cipher block dependent on the all other previous blocks. Decryption is simply the inverse of encryption, following the same steps but reversing the order in which the keys are applied. 64-bit key. DES uses a 64-bit key, but because 8 of those bits are used for parity checks, the effective key length is only 56 bits. The encryption algorithm generates 16 different 48-bit sub-keys, one for each of the 16 encryption rounds. Sub-keys are generated by selecting and permuting parts of the key as defined by the DES algorithm. Replacement and permutation. The algorithm defines sequences of replacement and permutation that the ciphertext undergoes during the encryption process. Backward compatibility. DES also provides this capability in some instances. Strength and security of DES. The following features enhance the strength and thus the security of DES. The first feature is use of 56-bit keys. 56-bit key can be frequently used in encryption. There are 256 possible keys. A brute force attack on such number of keys is impossible. A machine implementing 1 DES encryption per microsecond would take more than thousands of years to divide the cipher. If the text message has been compressed before encryption, then identification is more complex. The nature of algorithm. Cryptanalysts can implement cryptanalysis by exploiting the features of DES or data encryption standard algorithm. It can be exploring the weakness of 8 substitution tables or S boxes that are utilized in each iteration. Much of the work has been completed and the number of regularities and unexpected behaviors of the S boxes have been found, but no one has succeeded in discovering out the weaknesses in the S box. Timing attacks. A timing attack is a security exploit that allows an attacker to spot vulnerabilities in a local or a remote system to extract potentially responsive or secret data by acquiring the concerned system's response time to several inputs. A timing attack is a type of a broader class of attacks known as side channel attacks. Timing attacks allows an attacker to extract secrets maintained in a security system by acquiring the time it takes the system to respond to several queries. A timing attack accomplishes the fact that on encryption or decryption, algorithm takes different. Advantages and disadvantages of DES algorithm can be listed as follows. The advantages of the DES algorithm are: it is set as a standard by the US government. When compared to the software, it works faster on hardware. Triple DES used a 168-bit key, which is very hard to crack. The disadvantages of the DES algorithm are: weakly secured algorithm, there is a threat from brute force attack, and a DES cracker machine known as deep crack is available in the market. Hence, this module explains the DES in detail. The module discusses the history, structure and security of DES. DES uses a symmetric key algorithm for the encryption of digital data. DES follows the feasted structure, which follows 16 round functions, and it is insecure due to the relatively short 56-bit key size. However, the 256 possible keys made the brute force attack impossible. The timing attacks and the nature of algorithm made it more strong and secure. Hope you are clear about the topics discussed here. See you next time. Bye.